So I'm going to talk today about the resilience of ecosystems. Now, resilience is one of those words that has a different meaning depending on who you talk to, so I'm going to straight up define it. So resilience, in the way that I'm using it, is the capacity of a system to absorb shocks and adapt to change without changing into something that's very different, into a very different state or a different regime. Now, the state, or the system that we're examining, can either be an ecosystem, or increasingly people are looking at the resilience of societies, the resilience of economies, and at combinations of those two. So the centre that I direct, based in Townsville, has a program which focuses on the resilience of interlinked social and ecological systems. Often, when we look at the collapse of a system from one state into another, those shifts may or may not be desirable depending on whom you talk to, either different individuals or different segments of society. Many people think of resilience as a good thing that we should bolster. But if we're dealing with two alternative states, it may well be the case that there's conflict as to which system we would like to preserve. And in fact, it might be a goal of management and governance to undermine resilience of a system which was undesirable. So for example, if you found yourself in a landscape that had become salinated, that salinated ecosystem might be very resilient to future change, but it might also be undesirable, and your management goal might be to revert back to a system where the salinity in the soil wasn't as bad. So alternative states can either be desirable, and that's very much a value-laden term, or undesirable, and so management might seek to bolster or to undermine resilience. If we look around the world today, we see a biosphere that has been increasingly shaped by humanity over the last few centuries in particular. So in the sea we see altered food chains with fewer and fewer big fish and fewer fish. So many of the world's fisheries today are concentrated on this end of the food web. We've transformed the landscape, particularly with native vegetation being removed and replaced by aquaculture, agriculture, and cities, of course. And we've even changed the atmosphere. So this is the ozone hole at the South Pole. And increasingly people are referring to a new geological era, the Anthropocene, a period in Earth's history which is now dominated by just one species. So we've all heard of the age of the dinosaurs, but that was hundreds of species. We've never had a case in Earth's history, at least not since the Precambrian, since a single solitary species, namely people, is capable of transforming the planet to the extent that we have. One idea which is gaining traction in the recent literature is the idea that the impact of people globally has become so large that we need to set planetary boundaries to the impact of people, which raises the issue of what are the main drivers of ecosystem changes that we're seeing around the world today and in recent history. The primary one, of course, is human population growth and migration of these people. If we'd all stayed in Africa, then Australia and Europe would be a more pristine place than it is today. Another major driver, of course, is the wealth distribution and the consumption patterns, the manufacturing patterns of those people, and the role that evolving markets are playing today. Today, many commodities have become globalized. So if you catch a fish in Australia and want to sell it, it's as likely to end up in China or Singapore than it is to be sold within Australia. Those two major drivers are leading to a whole suite of changes in the landscape, in the seascape. We're changing biogeochemical cycles. Biodiversity is decreasing, so one of the main reasons for the concept of the Anthropocene is the unprecedentedly rapid rate of extinction of species in the last century or so. We've mentioned ozone depletion and other types of climate change that are sometimes referred to by managers of these systems as the threats. I prefer to think of them as drivers of change rather than threats, recognizing that one person's threat might be another person's livelihood. And the final point is that the scale of these drivers, which are anthropogenic, are now huge. People are affecting landscapes and seascapes at regional and even planetary scales. So the concept of planetary boundaries has recently been proposed, and a recent paper published in Nature suggested that we need to set limits for these 9 different systems. So a limit, for instance, on the amount of global warming, keep the Earth from warming more than, say, 2 degrees, or keep atmospheric CO2 concentrations below, say, 450 ppm. That paper that I'm referring to was by Johan Rockström et al. He wrote it with, I think it's 26 of his closest friends, and 3 of us, Will, Stefan, myself, I'm in there somewhere, and Brian Walker were the Australian contingent. So what we proposed is a simple conceptual model, which I've shown here. So if you think of drivers of change, which some people refer to as human impacts, or the stressors that are escalating through time, and the response of global ecosystems to those drivers, there's a response curve which is indicated here by this solid black line. Now, in many cases, we don't exactly know what the shape of that curve is. We know it's downwards, but we don't know how steep it is, whether in fact it does have a threshold or whether it's a more gradual response. But regardless of whether there is a tipping point or not, there is certainly motivation to avoid this level of change because of the degradation to the ecosystem, resulting in reduced ecosystem services being delivered to people. I'll talk a bit more about the concept of ecosystem services in a moment. So what this concept suggests is there may or may not be a dangerous threshold sometime in the not too distant future. There's a large degree of uncertainty about where that threshold might be. So the safest way for us to operate as a species is to define a safe operating space for continued human development. Now, this isn't about limits to growth. It's about safe places where human development and nation building can still continue, but avoiding the risk of long-term degradation to the environments that support human well-being. I've put this slide in here to make a number of points. It looks like a biology lesson, but I actually want to make a number of more broader points with it. First, let me explain the biology. So, sorry, wrong button. If we look on the picture on the right, this is a food web, and those of you who have any biology at all will know that these are different tiers within the food webs. There are top predators at the top of the food chain, and at the bottom are so-called primary producers who get their energy usually from sunlight. And the arrows depict the flow of energy, or basically who eats whom. And an ecologist like me can go out and measure these species and measure the strength of the arrows between them. So on the left here is a pristine food web before any people, or in a very remote place where people are still not a big part of the food web. But the more typical case is here, and you'd be amazed at how many food webs are published these days without the top predator being present in it, and that of course is people. So people have altered the structure of food webs almost everywhere. This is an example from my favorite ecosystem, namely coral reefs, but we could conceptualize a model very like this for almost any ecosystem on the planet. Okay, that's the biology. There are two ways of looking at this picture. You can say, oh my God, look at the terrible things all these people are doing to this poor, vulnerable, delicate ecosystem. And that's a common reaction. Or an alternative reaction is that, isn't it marvelous the way all these people are being supported by the ecosystem goods and services that are delivered to this ecosystem? So the ecosystem has gone from being a pristine system into what might be called a social and ecological system, where people are part of the ecosystem rather than being distinct from it, and where there are very strong interactions between people and that ecosystem. And if we're clever about it, these interactions can occur sustainably, and ecosystems like coral reefs can deliver food and other ecosystem services. Another point I'd like to make using this graph, although it looks like biology, basically what we've shown here is the kind of transition that has occurred globally across virtually all ecosystems during the Anthropocene, where we've gone from state A, which is pristine, to state B, which is a highly human-altered state. It begs the question, where are we going to next? We've gone from A to B. Next we're going to system C. And the reason I say that is because it's not going to be possible to stay here, and it's certainly going to be impossible to go backwards. The reason for that is that the world is on a conveyor belt. The human population is growing, consumption rates are increasing, the climate is changing. And that's quite confronting to think that we've gone from A to B and now we're going somewhere else, because it basically makes us examine concepts like preservation and conservation, which are about staying in B, or restoration, which is about going back to A. But those concepts are not credible at a global scale. We can certainly do them at a very local scale, but really what we should be doing is preparing and planning for going from A to B and now to C, because the transition from B to C is under our control. So do we want a C which is sustainable, which fosters human well-being whilst sustaining ecosystems, or do we want somewhere an alternative C which is a pretty bad place to be? And that's where business as usual is likely to take us. So you thought you were seeing a food web, but I want to make those other points as well. I've been interested in ecosystem change and shifts from one state to another for most of my career. And to me, the changes that have been occurring on many coral reefs throughout the world are not theory, they're personal observation. So this is a picture I took on the reefs in the Caribbean in 1976. I forgot to tell you that I started diving at the age of 3. 5? Anyway, this shows what Caribbean reefs used to look like about 40 years ago. They're dominated by these two species of branching coral. Those of you who know corals, that's Acropora palmata, or the elkhorn coral. This is Acropora cervicornis, or the staghorn coral. Those are the only two species of branching coral in the Caribbean. And today, those two species are on the endangered species list. They used to be so prevalent, as this picture shows, that this was called the Acropora palmata zone, and that's the Acropora cervicornis zone. And you can swim in those zones for kilometers and be surrounded by these two species of branching coral, which are now almost completely destroyed. So Caribbean reefs today look like that. This is all seaweed. So they've undergone a so-called regime shift. The resilience of this intact ecosystem has been undermined primarily by overfishing, but also by localized pollution, and it hasn't been helped by climate change. So it's undergone this transition. Now, I study reefs for many reasons. They're intrinsically very interesting and challenging as highly diverse ecosystem, but they're also very important socially and economically. So the red splotches here show the locations of the world's coral reefs, and you'll see that Australia has coral reefs around the top half of the continent. Australia has stewardship of about 12% of the world's coral reefs, which is a big chunk. Only 3 other countries have a little bit more than that. And uniquely among this tropical domain, Australia is a wealthy country. So Australia's capacity, and Ian alluded to this, to undertake coral reef research and coral reef management is second to none. And many other countries, particularly developing countries, look to Australia for advice and training. So coral reefs are important socially and economically, as well as aesthetically and for their conservation value. They support the livelihoods of about 250 million people throughout the tropics. And as I'm sure you're aware, many coral reefs are degraded. There's a project called the Global Coral Reef Monitoring Program, which produces reports on the status of the world's coral reefs about every 4 years. And the last report had this estimate that close to 40% of the world's coral reefs are so degraded that they're unlikely to recover in our lifetimes. And another third are increasingly threatened and have already lost about half of their coral cover. And included in that second category is our own, the Great Barrier Reef, which I'll talk about in a moment. So all of that was basically introduction to what I'm mainly going to be talking about today. So my talk will start out by talking about the status of the Great Barrier Reef. You may have read in the newspapers over the last year and a half or so that UNESCO, which is the world body responsible for World Heritage Areas, is concerned about the status of the Great Barrier Reef World Heritage Area. In particular, they're worried about coal port expansions and about climate change. So I'll examine some of those issues. Then, towards the end of the talk, I'll talk about government policies and management practices and whether or not they're working. And I want to say a few words about marine parks. Marine parks are the primary tool for management of marine ecosystems. They're somewhat controversial, and I'll address some of the issues around that. And finally, I'll talk very briefly about the future prognosis for the Great Barrier Reef. So if we focus on the Great Barrier Reef, we talked earlier about drivers. What are some of the drivers, the human activities, if you like, that are potentially changing the nature of the Great Barrier Reef ecosystem? So this is a Google exercise that I did recently, where I looked for information on 6 proxy metrics of human influence or drivers on the Great Barrier Reef. So the size of the Queensland population, the number of recreational boat licenses, the export amount of coal, the amount of fertilizer which is applied within the Great Barrier Reef catchment, and the amount of the Great Barrier Reef catchment which is harvested for sugarcane each year. And I scaled each of them from 0 to 10, where 10 is the maximum value of each of those metrics over the last century or so. So it's a pretty crude analysis. You could do it yourself with Google in an hour or two, which means it's reproducible. 2 points. First is they're all growing. The only one that's come down a little bit is the area under sugarcane cultivation. And the other point is there's more and more of them as time goes on. So the diversity of drivers today is much higher than the diversity of drivers a century ago. And there are new things happening like coal mining. Fertilizer application really took off from the 1960s and hasn't looked back since. So these are potentially affecting the Great Barrier Reef through fishing pressure, through CO2 emissions, contributing to global warming and ocean acidification through fertilizer runoff and through runoff of sediment and other nutrients. So what's the response of the Great Barrier Reef to some of those kinds of escalations in human drivers? Well, if we look firstly at these two maps, I realize you can't make out these keys, but basically green or blue in this figure means trees. And this was the land coverage or land usage in 1800. We know this from historical records, from pollen analyses in lakes. All sorts of information goes into these maps. And this is the situation today. So basically the catchment of the Great Barrier Reef has been cleared of most of the trees, and the way it's used today is fundamentally different from a century or 2 centuries ago. And that has had its consequences. Here's a picture taken in 1883 and the same location a couple of years ago. So if you look at this mountain range in the back, that's the same place in both pictures. So this is a very healthy looking reef. It's got about 80% coral cover. It's dominated by branching corals called Acropora. Today that same location is a mudflat. These bumps out here are actually dead corals. And you can collect these dead corals and age them. So we know that most of these died between about 100 and 150 years ago, some more recently. When I saw that picture for the first time, I just about fell off my chair, because as a coral biologist, to me that looks like an assemblage of corals, a mix of coral species that today you would see on an island or on a reef 30 or 40 kilometers from shore. But this is the mainland of Australia in 1883. So many of the coastal reefs that were present when Captain Cook sailed along the Queensland coast today look more like this. So there's been a very substantial loss of fringing nearshore coral reefs, which used to be part of the Great Barrier Reef, but which today we scarcely even recognize as once being reef environments. Another issue related to runoff of nutrients from land and changes in catchment use is outbreaks of this creature. This is the crown of thorn starfish, Acanthastor. The first recorded outbreak of crown of thorn starfish started in the early 1960s, and it had a huge impact ecologically, but also politically. That outbreak and a second outbreak, which occurred about 15 years later, were instrumental in the formation of the Great Barrier Reef Marine Park, because people were really concerned about the damage that this starfish is causing. As you can see from this picture, it eats corals, and it's not really fussy about which corals it eats. So if you get a few million of these on a reef, they can be incredibly destructive. The most likely cause of those outbreaks is elevated nutrients in runoff from land, resulting in more phytoplankton. Phytoplankton is the diet of the larvae of these starfish. And if you feed starfish in the laboratory, if you add more food to their diet, they develop far faster. So instead of 10,000 settling after a month, if you feed them, you get 10 million after 3 weeks. And that's almost certainly the cause of these outbreaks, which are linked to flood events where we get a big pulse of nutrients coming off the reef. So what are the responses of the Great Barrier Reef ecosystem to escalating drivers like the ones I've been discussing? For a start, we've seen a big decline in the megafauna and also in seagrasses and corals. By megafauna, I mean big things like sharks, dugongs, turtles, crocodiles. For example, the number of dugongs on the Great Barrier Reef in the lower 2/3 of the marine park has declined by 98% over the last 30 years. The decline of loggerhead turtles is about 75%. So these are very significant decreases. I'll come back to corals in a minute. As a consequence of losing the biggest herbivores and some of the biggest predators on the reef, the food webs have changed, and we talked just a moment ago about the domino effect of added nutrients, more phytoplankton, more crown of thorns, less corals. That's another example of an altered food web. We've also seen increased levels of bleaching due to global warming, more coral diseases, and more starfish. So we're now in the beginning of a fourth outbreak of crown of thorns starfish, the fourth since the early 1960s. That's too many. It's not sustainable for the Great Barrier Reef, given the rate of growth of corals, for there to be that number of outbreaks at that high frequency, which suggests that crown of thorns outbreaks are not a natural event, but that they're being spurred on by nutrient addition. And the result of all of this is a loss of resilience to natural events. So that picture I showed you before of the old photograph and the new one, clearly that reef in the 1800s was able to cope with recurrent cyclones that come across the reef every couple of years in any particular location and bounce back. But it has now lost that capacity to bounce back because it's locked in to a muddy alternative state, and it has lost the capacity to bounce back. Turning to coral cover on the Great Barrier Reef has been quite extensively studied. Here are 4 studies published in the last decade or so. They looked at coral cover in different periods. This first paper was published in Nature, and basically they all showed the same thing, which is that more than half of the coral cover on the Great Barrier Reef has been lost over the past 50 years. Now, most of that loss is on reefs that are closer to shore, and most of it is on reefs that are south of Cairns. So the best reefs on the Great Barrier Reef today are further offshore and further north. They are the backbone of the tourism industry. So I'm certainly not painting a picture here where the Great Barrier Reef is on its last legs. But I do want to make the point that the Great Barrier Reef is certainly not a pristine system. It's a highly altered system, and it's now quite patchy in terms of the degree it has changed in recent decades and centuries due to human activities. Another issue for coral reefs everywhere is global warming. So this is a picture showing coral bleaching. Coral bleaching has occurred on the Great Barrier Reef extensively twice in recent decades. In 1998, which, as you might recall, was a very warm year, and again in 2002. The frequency of bleaching events is increasing globally. They were unknown before the mid-1980s. They were first recorded in the Eastern Pacific and the Caribbean, which are closer to the epicenter of El Nino events. And so it's virtually a certainty with rising temperatures, increasing sea surface temperatures, that we'll be seeing more of these bleaching events in the future. It's very difficult to directly manage bleaching events because the driver, namely global warming, is by definition global. But there are things we can do locally to bolster the resilience of the reef, to try and cope with some of these larger scale impacts. Now, this picture here is perhaps a little bit deceptive in that it shows just one species of coral. This is a branching coral, and that's one big colony, one genotype. A more typical picture would show more of a checkerboard effect where some corals are bleached and others aren't. And that's important because bleaching is very selective. So this branching species is obviously very susceptible to bleaching. But if we look at a suite of species, which are shown here, that's a more typical photograph where we have bleached and unbleached corals. So this is a range of species. I've spared you the Latin names. I'm going to call them A, B, C, and D. And this is the percent that were bleached during this particular bleaching event. So the last picture was a species A, an Acropora, that's very susceptible. But if we look at these other species, there are species I and J that didn't bleach at all. Now that's important because there are winners and losers in almost every human impact we can think of. So some corals or seagrasses are more susceptible to sediment than others. Some respond more than others to nutrient runoff, and some respond more than others to global warming. So in the future, we can expect these species to become more dominant, and we can expect those species to become less prevalent, and that's already happening. Climate change, to a coral biologist like myself, isn't some distant threat that we'll start to measure in 20 years. We have been measuring it since the mid-1980s, and already we're seeing quite striking shifts in the mix of species, corals and others, on reefs around the world as a response to climate change. So it's not just the case that the coral cover goes down and down and down, and all species are equally impacted. It's a more subtle shift than that, where the mix of species is changing. So I'm perhaps a little bit more optimistic than some coral biologists in the long-term capacity of reefs, including the Great Barrier Reef, to cope with the impacts of global warming through this mechanism of shifting the mix of species. I want to move on now and talk about this second bullet point, which is basically a focus on how is the Great Barrier Reef managed, and is that management strategy effective? Is it working? So the main way that the Great Barrier Reef is managed today is through a system of zoning. Now I realize you can't read all the words on this, don't try to. There are 7 different zones. So if you think of a map of the Great Barrier Reef, I'll show you one in a minute, that's colored these different colors. This is a list of the things you could possibly do within the Great Barrier Reef, or most of them anyway. You could go fishing, you could go diving, you could go trawling, you could collect things, you could do research, and so on. It's a long list. And this is whether or not you can do them with or without a permit inside each of these zones. So the pink zone here is the most stringent. You can't even go into a pink zone. It's an exclusion zone. There are very few of them. They're primarily designed to keep people away from rookeries for birds, or nesting sites for turtles. The next zone type is called green zones. Green zones are no fishing zones. They're the ones that are the most controversial. And now about 1/3 of the Great Barrier Reef is zoned inside the green zones, and you can't fish there. I'm not going to go through them all. Yellow zones, you can fish if you're a recreational fisher, but you can't fish if you're a commercial fisher. And blue zones, you can do pretty much anything, although sometimes you need a permit to do it. So this is the way that the Great Barrier Reef has been zoned since zoning began way back in 1976. The zoning of the Great Barrier Reef was transformed in 2004. So this is a map of the Great Barrier Reef Marine Park. It doesn't look very big on a map like this, but it's actually the same size as Italy, to give it some perspective. So it's up to about 250 kilometers wide, and it's about 2,000 kilometers long. Prior to 2004, only 5% of the Great Barrier Reef Marine Park was green zones, and most of that was up in the very far north, a very remote place. And the reason for that was social and political. That's what was feasible in the 1970s. But more recently, public support made it more feasible, and also more and more scientific information about long-term trends in the Great Barrier Reef made it more and more urgent to increase the level of protection on the reef, because the Great Barrier Reef Marine Park Authority came to the conclusion that their existing level of protection for the reef was inadequate. So in 2004, through an act of the Commonwealth passed by both houses of Parliament, the reef was rezoned. And so the amount that was in green zones increased from 5% to 33%. And you can see that today the coverage of green zones is much more widespread. It's a much better system. And one of the attributes of a network of green zones like this is that the green zones can talk to each other. In other words, they can function as a network. They can exchange larvae. So a species that's breeding up here can exchange larvae with the same species that's breeding up there. And if something bad happens to that green zone, like a bleaching event or a flood or a ship grounding, then there's a potential for it to be rescued over time by adjoining green zones that are otherwise protected. So some of the benefits for marine zones are listed here. They protect habitat and conserve species, obviously. Somewhat more controversially, they're thought to enhance fisheries. I'll come back to that point in a moment. They provide insurance against environmental uncertainty, which I mentioned in terms of that rescue effect a moment ago. And obviously, they keep a nice, healthy habitat, which is an attractive place for the tourism industry. And tourism on the Great Barrier Reef is worth $5 billion a year. It's a huge industry. It's a much, much bigger industry compared to either recreational or commercial fishing. Looking around the world, there's a lot of evidence for the benefits of these marine reserves or green zones. So this is a compilation of studies. So each dot on here represents a peer-reviewed study in the literature, and these are different attributes that marine reserves contribute to. So if we look at the size of fish, there's an average of an 82% increase inside marine reserves compared to outside. Now that's not rocket science. If you leave the fish longer in the water, it will tend to survive and grow. So the density of fish, the number per hectare, tends to double, and the biomass, which is these two together, goes up by about 400% on average. Some places go more, other places show a much more modest increase. And obviously there's a species protection role as well. Most of this data comes from other places around the world, but since 2004, my colleagues and I have been able to use the rezoning as an amazingly well controlled experiment that's suitably replicated with before and after comparisons and comparisons between these different zones. So we've been able to, much more rigorously than this analysis here, look at some of the advantages of these green zones and other zones. So here are a couple of examples of that. So these are two studies done by these people and those people where they looked at the number of sharks per hectare inside these different zones. So there's the pink zone, no entry, the green zone where you can't fish, the yellow zone where you can fish recreationally but not commercially, and then the fish zone. So these are basically a gradient of stringency of fishing regulations, if you like. And it creates this step of stairs. So we get the most sharks inside the pink zones for these two different species. Both studies found the same thing. We go from pink zones to green zones. There's a stepwise decrease, but there's still more sharks in the green zones compared to the yellow or the blue. So they work. The higher the level of protection, the better. An interesting point from this graph is that you're not allowed fish in either the pink or the green zones. So in theory, the number of sharks should be the same. But it isn't. Pink zones protect sharks much more. What do you think that is? It's probably got to do with poaching. So if you're in a pink zone, if you're physically there and a surveillance plane passes overhead, you're done. They'll have a digital photograph of you and you'll be in court the next day. But you're perfectly entitled to be in a green zone. So if you hear the plane coming, you hide the rod. So I can't think of any other explanation for why this disparity would occur. If we look at the green zones versus the blue zones, this time for the most important commercial and recreational fish rather than sharks, we get a huge disparity. It's typically about fourfold in the biomass of fish. This is kilograms per 1,000 square meters, inside versus outside. So these green zones are really, really effective. The controversy arises because recreational fishermen in particular don't have access to green zones, at least not legally. And the question they often ask is, what bloody use to me is a green zone? It might have all the fish in the world in it, but if I can't fish them, I'm now being restricted to blue zones and also to yellow zones, and that's a disadvantage to me, so I don't support green zones. It's a common argument. The counter-argument goes as follows. Inside the green zones, we now have more fish and they're bigger. So within 3 years of the rezoning in 2004, the amount of fish doubled. I'm talking here about coral trout. And a lot of that doubling was an increase in number due to new recruitment, but some of it was due to growth of corals because the mortality rate for fishing is sharply reduced inside the green zones. Now, an important issue here is the relationship between the size of fish and the reproductive output they have, the number of babies they produce. It's not a linear relationship. So as you go from small to medium to large to very large in fish size, there's a disproportionate increase in the number of baby fish that the larger fish are producing. So if you only have a few small adult fish, there's not much reproduction. But if you have more and bigger fish, you get a much greater level of reproduction. And that's important because of the distances that these baby fish travel. So the issue here is something called connectivity. So this is a green zone with more fish and bigger fish compared to the surrounding seascape. The question is, how many of these baby fish are being exported? That export is potentially very important because it could sustain the ongoing fishery outside the green zones, in the blue zones, in the case of the Great Barrier Reef. Now, this has been an unsolved question for the last 20 years as more and more marine reserves have been established. And just in the last year, the researchers in the center that I direct have been tackling this issue. So here's a graphic that summarizes this problem. So if this is a green zone, that's a blue zone, and this is another green zone, we really need to answer these questions. How many of the larvae produced here come back? Is this green zone self-sustaining? Will it look after itself in terms of being able to reseed itself? Another issue is how many of these larvae from these big mamas are reseeding the depleted populations where fishing is continuing in the blue zones? And a third issue is, do these green zones talk to each other? Do they act as a network? And so we can put numbers on these circles, which is shown here. So this is data from a paper published by Jeff Jones in Current Biology about a year ago, where he used tagging. He teamed up with some recreational fishing clubs on the southern Great Barrier Reef, and they tagged huge numbers of adult fish, and they mapped where their babies were going using genetic tags and paternity analysis for fish. And they looked at these two species that are commercially important. And these are the sort of numbers that they found. So yes, the green zones do self-seed. They export a phenomenal proportion of their larvae into the depleted fished areas surrounding them, to the extent that more than half of the larvae in the blue zone is coming from these protected green zones. And that proportion is expected to increase through time as the stocks in the green zones continues to increase. And finally, the green zones are working like a network. They're exchanging larvae. So the point I want to make is that these green zones are often criticized for locking out fishers and for pushing them aside into other zones. But there is a spillover advantage, an impact on the broader seascape of building up reproductive stocks within these green zones. A final point I want to make, coming back to this zoning table, is that although there's a huge list of things you could potentially do in these different zones, there's a few activities that are missing. And in particular, some of the new activities aren't on there. So there isn't a zone for dredging. There isn't a zone for anchoring a coal ship. And you can think of lots of other newer things, new industries in many cases. There isn't a zone for dumping dredge spoil, which is a particular concern of UNESCO in terms of the status of the World Heritage Area. So I want to just briefly look at dredging. I mentioned earlier that the runoff to the reef has increased because of changes in land use. So we have pretty good estimates of the amount of runoff to the reef that's occurring today and in the past before the catchment was changed. So today about 9 million tons of sediment come down all of the rivers and run onto the coastal reefs and into the lagoon of the Great Barrier Reef. Historically, that amount was about 3 million tons before all the trees were cut down. So about 6 of the 9 million, or 2/3, is, if you like, added runoff due to anthropogenic impact. In the last few years, the Commonwealth Government, in collaboration with the State of Queensland, has initiated a program called Reef Rescue. Reef Rescue is an attempt to reduce runoff of sediment and nutrients from the Barrier Reef catchment into the reef. It was initially a $300 million 5-year program, and there's a new $200 million program hopefully underway soon. And that program has had some modest success, and in 2012, after 3 or 4 years of operation, some modeling suggests that investment had reduced runoff by about 360,000 tons. That's about 5 or 6% of the 6 million. So it's a step in the right direction, albeit a fairly small step. Now, I've put these figures up because I want to compare them to the amount of sediment which is being proposed to be dredged and dumped on the Great Barrier Reef, which is this. So if all of the port expansions that are currently in the pipeline and being proposed go ahead, which is probably unlikely, then the maximum amount of dredging over the next decade and dumping of dredge spoil is about 200 million tons. So that's 200 compared to 6, 9, and 3, or 360,000. It's a huge amount of sediment. If that was discharged over a 10-year period, then it'd be about 3 times the amount that's currently going onto the Barrier Reef, which is the elevated amount, or it's about 6 or 8 times the amount that the Great Barrier Reef historically received before about 100 or 150 years ago. It's hard to envisage what 200 million tons of sediment looks like. If you think of the 2 largest suitcases in your home, the 2 you would bring to Europe if you were going for 6 months, that's probably close to a cubic meter. So if you think of 400 million large suitcases, it's a lot of sediment. So I think, as a nation, we need to be very concerned and rethink this whole issue of dredge spoil and how much the Great Barrier Reef is capable of sustainably receiving. There are other alternatives to dredging and dredge spoiling. You can put the dredge spoil on land, or you can build piers rather than trenches for the ships to gain access to loading docks. Okay, final slide. Climate change, runoff, dredging, and over-harvesting are the 3 big issues that are affecting reefs around the world, including the Great Barrier Reef. One point I'd like to make is that we have to address all of these drivers in order to get a sustainable outcome. Currently, we're dealing very effectively with one of these drivers, namely overharvesting. So the rezoning of the Great Barrier Reef has been very effective in protecting fish stocks inside the new green zones, and in also rebuilding and sustaining ongoing fisheries in zones where fishing is still ongoing. But in terms of climate change, we've done virtually nothing to deal with the risk to coral reefs. Runoff, there's been some modest improvements through government programs that hopefully will continue. Dredging has a big question mark over it, and I've outlined some of the risks of the scale of dredging which is being proposed for the Queensland coast. Prevention is better than cure. That's one of the lessons of resilience and understanding the dynamics of ecosystems. When a coral reef flips from a healthy coral reef to a degraded state, it's virtually impossible to bring it back again. And that picture I showed you from 1883 to the mudflat of today, that's a permanent transition. It's not going to come back, at least not within my lifetime or my children's lifetime. So prevention's better than cure. Finally, a more optimistic point. I've tried to argue that the Great Barrier Reef isn't doomed if we act quickly. I don't prescribe to the opinion that it will all be dead in 30 years. If that was really true, then we could all go and have some stiff drinks and give up. But I don't think we should give up. I think there are things we can do, things we are doing, which we need to continue. And if we look after the reef, it will still be there for future generations. The decisions we make now on coral reef protection are obviously going to have profound long-term consequences. And over the next 20 years, we've probably got a fairly narrow window of opportunity to deal with runoff, to deal with projected dredge spoil dumping, and to deal with climate change. So I hope that the future of the Great Barrier Reef is increasingly factored into the societal debates that we in Australia are having now about the need to reduce CO2 emissions. And it's always struck me as ironic that the state of Queensland has stewardship of the largest coral reef in the world, but also 200 years reserves of coal. And it seems to me that we need to make a choice between those two. Thank you.